Hello, calculus type people. Been a while. Hope you're having a fantastic day. We're going to get right into it. The area between two curves is what we're going to be talking about today. It's a relatively simple process. I've got a graph to show you real quick. This is a graph of x squared, the parabola, and the square root of x, your parent square root function. And here's the idea. Let me zoom in for this part. I want to figure out the area between these two curves, right? I want to figure out what this area right here is. So here's how I would do it. What I'm going to do is figure out the area of the curve that's on top, which is, I shouldn't have done that just yet. I'm going to figure out the area of the curve that's on top, which is this guy, right? And I'm going to subtract out the area of the bottom, which is this guy. And you can kind of see that what that's going to leave me with is this little leaf-looking shape. So over to the side of this graph, I'd like you to take a note really quick, and that is to find the area bounded between two curves, or bounded by two curves. Now this can be more than two curves, which we can get into later, but for right now it's just two. What we're going to do is take the integral of the top curve and subtract the integral of the bottom curve. Right? Now, because integrals are the way that they are, what I can do is actually just call this the integral of the top minus the bottom and kind of combine it into one integral, right? So that's where we get the idea at. And there's a statement right below here that kind of goes over that. It says, find the area of the region bounded by the two curves above. So it's A is equal to your first x value to your second x value of the top curve minus the bottom curve. Now what these x values are the intersection points of those two graphs. So if I look up here, I've got 0, 0, and I've got 1, 0. So my first job would be to figure out where these two graphs are equal to one another at. And again, there's two ways to do that. I can also come over here and say x squared is equal to the square root of x, right? And then I can figure out those two values, set them equal to one another, and solve for x. But I already know where they're at because they're parent functions. It's pretty easy. So I'm going to set this up for you real quick. This is the area from 0 to 1 of the top curve minus the bottom curve. Now the top curve here, I'm going to do parentheses, is the square root of x minus x squared dx. So I'm going to set up the top curve, and you know what, let me put parentheses around the curves themselves instead of around the whole thing. That might help a little bit. Dx is where the integral stops, so you know that. And I say put the parentheses there just in case there's some extra terms in that second function. It'll let you take that negative and kind of get it to all the parentheses. Now I do have a calculator handy with me. I'm not going to need it on this particular problem, but I'll need it a little bit later. So what this is going to be is the integral. I'm going to rewrite this 0 to 1, x to the 1/2 minus x squared dx. So after you distribute your negative, you can drop your parentheses. Right, and that's going to be, the integral of x to the 1/2 is 2x to the 3/2 over 2, or excuse me, over 3, minus x to the 3 over 3, evaluated from 0 to 1. Right? So your area is going to be, plug in a 1 and you get 2/3 minus 1/3. That's f of b minus f of a is 0. When you plug in a 0 here, 0 minus 0 is 0. So 2/3 minus 1/3 is 1/3. So the area between two curves, do the top curve minus the bottom curve. Okay. Example 2, I'm going to click right through these here pretty quick, pretty good pace. It says find the area between y equals 2x minus x squared. Now just to rewrite that, that's negative x squared plus 2x. And y equals x squared. All right, so that's y equals x squared. Okay, now there's a couple of ways that I could do this. I'm going to sketch a graph over here. Let me see if you can see this. What I'm going to do is I'm going to sketch a graph to see what's on top and bottom. So sketch to see, this is a visual helper. Sketch to see what's on top and bottom, because sometimes it's a little misleading. So let's sketch a graph here. It doesn't have to be accurate, so let me figure out what the zeros of this graph are. Let's see, we take out x, you can divide by -1, get rid of all that junk for all I care. Let's say 0 is negative x and x minus 2. So x is going to equal 0 and 2. So this guy, 0, 1, 2, is coming like this, right? And then from here, x squared, y equals x squared is just this guy. I've always known what that looks like, right? Now I do need to figure out where these two things hit, and you can do that. I mean, you can set up and see where they hit. With a calculator, you can do it by hand. I'll do it by hand over here on the side just to kind of show you real quick. Let's say 2x minus x squared is equal to x squared. Add x squared, or excuse me, subtract your x squared over. Now let's add it. Let's get everything over here. This is going to be 0 is equal to 2x squared plus 2x minus 2x, excuse me. Oh, let me get that over. I brought these two things over so I can have all positive values. Factor out 2x out of both, so 2x and x minus 1. So you've got x is equal to 0 and 1. So when x is 0 and when x is 1, these two graphs are going to meet. That means here at 0, 0, and then here at 1. And if you remember, you can plug in 1 into either one of these and get 1. So the point they meet is 1, 1. That's the hard part, is figuring out where these two graphs meet. The rest of it, piece of cake, piece of calculus cake. Area is going to be the integral from, and I want this region right here. The integral from 0 to 1. Where is it going from? Where is it going to? All right, and then I'm going to set this thing up here. It's going to be 2x minus x squared minus x squared dx. All right, and I'm not going to use a calculator here. I'm just going to go ahead and throw this out there. Area. Oops, let's go ahead and we can actually drop this. If we combine them both, we can combine this to 2x minus 2x squared, make it a lot more simple. Dx, which is going to be 2x integrated is going to be 2x squared over 2, which is just x squared, minus 2x to the third over 3. Evaluated from 0 to 1. And again, the 0 is just pretty much going to go away here. So I've got 1 minus 2/3. Fantastic. And then minus 0, f of b minus f of a, which is 1/3. Now, you can do this on a calculator. On your calculator, just really quickly so you can make note of the steps. Please write these steps down, but you just hit math number 9. And it'll pop up with either the integral sign or it'll say fn int, and you just have to enter it in with all the commas. But we're going 0 to 1. I'm going to try and update everybody's calculators so you'll have the newest and greatest and best. And I can do 2x, and you can do the simplified version or you can do the regular version. If you want to do the regular, 2x minus x squared, and then minus x squared dx, 1/3. All right, so it can be done with the calculator, sure, why not? All right, so the rest of these are going to be just really just setting up different scenarios, and there's one more kind of weird situation we're going to talk about. Example number 3 says, find the region bounded by the curves y equals sine x and cosine x, x equals 0, and x equals pi over 2. So let's start by graphing. I'm bounded by obviously the x-axis here, because that's what we're always bounded by. But we're going from 0 to pi over 2, basically. 0 to pi over 2. So here's pi over 2. All right. Now this one's actually a little bit interesting. I'm stopping at this line, pi over 2, right? Cosine x, cosine of 0 is 1, right? Sine of pi over 2 is 1. Sine of 0 is 0. Cosine of pi over 2 is 0. So these things look kind of weird. They look kind of like this, right? Kind of like a weird flag kind of an X. And I want the area between the two graphs. Now, identifying the area between the two graphs here is what's important. So I want the area between these two graphs. All right? So that brings me to an interesting point here. You have to break the integral into two integrals because the top and the bottoms change. All right? So I want you to make a little star here. Must break into two integrals because top and bottom change. Because we have to do the top minus the bottom, but here sine is on bottom, here cosine is on bottom. So I'm going to say that my area, and where does this break happen at? It happens right here at pi over 4. That's where cosine and sine are the same, right? Remember unit circles at pi over 4? They're both square root of 2 over 2. That's this point right here. Yeah? Yeah. The integral from 0 to pi over 4. And that's going to be top to bottom, so cosine x minus sine x. Always in parentheses just in case. And then I'm going to add the integral from pi over 4. That is an ugly integral sign. Oh my goodness. The integral of pi over 4 to pi over 2 of sine x, top, minus cosine x, the bottom. So I'm going to break this into two integrals. Now for the rest of these, because I'm dealing with some weird values, I'm going to use my calculator on this, and let's figure out what this is going to be, because it's going to be kind of a weird value. So I'm going to make sure that my calculator's on and in radians. I'm going to cheat. I've actually already done it, so I'm just going to give you the answers. It's 0.828. But you know how to enter that into the calculator. I'm not going to insult you and make you waste time doing that. Just remember that if your curves ever change positions, this one was on top, this one was on bottom, and then they switched, wherever that point is that they crossed and switched places at, I have to integrate from here to this point, and then from this point to the rest of it. All right. Number 4. It says, find the approximate area of the region bounded by the curves. And this one's kind of weird, so we're going to have to use the calculator to get the graph. But I'll give you a quick sketch of what it's going to look like. Let's see here. And I've already done this, otherwise I'd go through and do it right now as well. But it's this, and it's this, and it's this. It's kind of weird, but the important parts are that they come together at 0, 0, and over here at 1.181, whoa, comma, 0.763. That's the important pieces of information. So as you can use your calculator, absolutely, come up with the two intersection points. That's fine. That's absolutely fine. A problem like this would usually only be given on the calculator portion anyways. So your area is going to be the integral from 0 to 1.181 of x over square root x squared plus 1 minus x to the fourth minus x. This is where it's important to put them in parentheses because that negative will have to go to the x to the fourth minus x as well, dx. And I've already kind of set this up. I've already figured out what all these are ahead of time just for the sake of the length of the video. It's 0.785. But what I would like you to do is just write this down. This is the general calculator method. Again, it's Math 9 gets you to fn int, and you set it up with y1 minus y2. And if you do not have the updated software, you'll have to do comma x, comma 0, comma 1.181. I know a few of you who have your personal calculators or an old one checked out may have the older software, so I want you to have this handy. Be careful typing it in, and man, you're ready to go. Okay, number 5 is the last one here, and it's a little different, but it's the same concept really. Example 5 says, find the area of the region bounded by the graphs x equals 3 minus y squared, and y equals x minus 1. This guy, okay, first, if you set this thing up and you solve it for y, you've got y squared is equal to 3 minus x, right? You square root both sides, you've got y is equal to plus and minus the square root of 3 minus x. Ooh. This one is going to be pretty interesting because this is like an inverse graph. It's something graphed on the x-axis instead of the y-axis, which is funny. Let's graph this thing real quick. And you can actually, if you want to get an idea of what it's going to look like, let me plug this in for you real quick. I've got the square root of 3 minus x, and then the negative square root of 3 minus x. And then I've also got the curve x minus 1 from over here, x minus 1. Now just take a look at this. And what I'm trying to get is this area right here. Let me zoom in a second. Too much. -5 to 5, -5 to 5. What I want is this area right in here. Check this out. Bam. I want this guy. This area right in here. Now that's going to be a little weird. Let me go ahead and transfer this over onto my paper here. 1, 2, 3. It goes out to 3. And like this. And then x minus 1. So here's 1. Alright, now what I'm going to figure out real quick, just to make sure, I'm going to go and trace, or second trace, intersect number 5. Oh, nope, that is not what I wanted. Second trace, quit, whatever. Second trace number 5, and I'm going to pick this one and this graph right here. And I'm going to figure out, to bounce between graphs, you just press the up and down keys. I want to figure out where they intersect. It's at 2, 1. So this point right here is 2, 1. This point down here is -1, -2. I've already figured this out ahead of time, but I wanted to show you how I got it. Okay, now if you ever get a situation where there's not a top graph, there's a left and a right graph, there's a left hand and a right hand side, like this one, there's not really anything on top. There's just a left and a right. Well, we always do it bigger minus smaller, and on a graph, right is bigger. So you do the integral from y1 to y2. We are using our y values now of the right curve minus the left curve with respect to y. Now calculator-wise, it doesn't make it any more difficult. It's the integral of y1 to y2. So my y1 value is bottom to top, -2 to 1 of the right curve, which is this guy, right? So the right curve is x equals 3 minus y squared. Since I'm dealing this with reference to y, let's go ahead and get this other one in terms of x as well. X is going to be, what would that be, y plus 1? So what I'm going to do here instead is integrate with respect to y. So I have to integrate with my y values. My right curve is the 3 minus y squared minus my left curve is this y plus 1 dy. So everything is with respect to y now. Now again, it doesn't change your calculator steps anymore. You're still going to math 9, and it's -2 to 1. Oops, that's what I get. -2 to 1. And when you go to integrate, it should, I hope, I've already done this once, this should be okay. Y squared, yada yada yada, minus, no, this may have to be with, well, let me try it. I've forgotten how I plugged it in. I think this worked. If not, I'll correct it in class sometime. 4.5. Perfect. That's what it is. So I just plugged it in with x instead of y. It doesn't really matter. Obviously it matters when you go to graph it, but all this is doing is really just graphing it this way and flipped around if I do it like that. But either way, calculator doesn't know any better, so 4.5. This one takes a little bit of getting used to, so we're going to do quite a few of those when we get to class, and I'll clear up any questions in a while.